DC circuits stands for direct current circuits. So we're going to plug into either a battery or a power supply, and current is always going to be flowing the same direction through this circuit. With this, there's two things we want to do in this video. I want to teach you how to calculate what the voltage and the current will be at various locations in a circuit. And then I want to teach you how to use a multimeter to actually measure the voltage and current at different places in a circuit. And I think that if you like Sudoku, you will love resolving composite circuits. A composite circuit is just where there's lots of different resistors and in series and in parallel, and it can get a little complicated. But it'd be like I'm giving you that this is 12 volts, there's all these resistors in these different places, and I would like to say how much voltage does that one get and how much current is there right there. And I will say that we're not going to do anything quite as complicated as this, but the basic principles that I teach now could apply to that. In order to get a full understanding of composite circuits, there's a new visualization I want to make as a diagram. So let me just make this comparison. That we had gravitational potential, that's how much energy there was per kilogram. And if you raise that up, pushing it against the gravitational field, you've raised its gravitational potential energy. Similarly, if you push these charges over here against the electric field, you have raised the electrical potential of those charges, and that would be how much energy there is per Coulomb. And then if you just let go of that mass and let the gravitational field drop that down, it will drop the gravitational potential. If you put a wire between these two things and let that electron zip back through a resistor, when it goes through that resistor, it's dropping the electrical potential. It's getting back down kind of like to the ground. So that's where these diagrams come in. I'm going to represent a voltage of a battery as raising the potential, going up these stairs, and then going downstairs would be like going through a light bulb that had resistance. It's going to drop the potential. And Kirchhoff's loop rule says that if you go around any loop, if you go around this loop, or you go around that loop, or you go around this whole big loop, the total raise in potential should equal the total drop in potential. And we see it like this. This is the Greek letter epsilon, and it stands for electromotive force. That's what the batteries do. They push on these charges. And electromotive force is measured in volts. And if there's an electromotive force of 6 volts, it would cause a difference in potential of 6 volts. It's kind of like when we had impulse and momentum. An impulse of 6 Newton seconds causes a change in momentum of 6 kilogram meters per second. All this is saying is that the total raise in potential should equal the total drop in potential. Because when you send current through a resistor, current times resistance would be the drop. So raised it, dropped it, dropped it. And that's going to be true for any loop. And that makes sense. Just if we start here and we go around the loop and we get back to there, the total steps up should equal the total steps down. And then I just want to remind you about Kirchhoff's junction rule, that if we have a split where either different paths are coming together or one path is split into other paths, the total current coming in should equal the total current going out. Now this is just a simple schematic diagram. These little jaggly lines here represent a resistor. This is a battery. The long end is the positive side of the terminal, and the short end is the negative side. So we've just got 1 ohm, 2 ohm, and 3 ohms, and we would like to place an amp meter right there and measure how much current there's going to be there, there, and there. We'd also like to place a voltmeter and measure the difference in potential from here to here and there as well. So that's what we're going to work on right now, is figuring out what these values are. Given the voltage and each individual resistor, how much current is there and how much voltage is there in different places. I want us to be able to see that this schematic diagram here is nicely represented by these stair steps. The stair steps going up would be a battery providing electromotive force, pushing these charges up, giving them electrical potential, and then when current goes through a resistor, it drops the potential. And that would be like using the energy of those charges to make light or heat or something else. First thing I'm going to do is figure out how much current is going through there. In order to figure out how much current is going through there, it's going to depend on how much resistance there is overall. So these are just 3 resistors in series, and it's just 1 plus 2 plus 3. There's a total of 6 ohms of resistance. And this is Ohm's law. So if we had a total of 12 volts across a total of 6 ohms, we should get 2 amps of current. So the 2 amps of current is going to be going through the battery. It's 2 amps here, it's 2 amps there, it's 2 amps there. There's 2 amps everywhere. But now that I know that it has 2 amps, I can find out the voltage that each of these gets. Because if you take Ohm's law, there's 3 variables in it. Anytime you know 2 of the variables, you can solve for the third. I'm just rearranging this equation to solve for the difference in the potential. So if I had 2 amps running through 1 ohm, 2 amps running through 1 ohm, it would drop the potential by 2 volts. And 2 amps running through 2 ohms would drop it by 4 volts. And 2 amps running through 3 ohms would drop it by 6 volts. I often have students ask me, well, how do the charges know to drop it by 2 here and 4 there so that it can drop it by 6 here to get back to nothing at the end? It's a good question, but the charges don't know anything. How much voltage it drops depends on how much current there is and how much resistance there is. Let me redraw this circuit and without the 3 ohm resistor. I'm just going to have the 1 ohm and the 2 ohm, and I'm going to just eliminate that one. This is what it would look like. Now, it looks like it's going to drop the voltage more for each to get back to that same level, but why does it do that? Well, the batteries raise the potential, the resistors drop the potential. The total amount of current running through here depends on the resistance. This time there's only 3 ohms of resistance. Before there was 6 ohms of resistance. So using Ohm's law here, a voltage of 12 on this time a resistance of 3, there's going to be 4 amps of current running through here, twice as much current. So we're going to get 4 amps running through here and 4 amps running through there. More current on that resistor. So this time if I have 4 amps and 1 ohm, it's going to drop it by 4 volts. If I've got 4 amps running through 2 ohms, 4 and 2, it would drop it by 8. So the amount that it drops it really just depends on how much current is running through those resistors. Now let's look at 3 resistors in parallel with each other. And we'd like to measure how much current is there, and here. And we'd also like to measure the voltage here, there, and there. I hope we can already see that the voltage for this one, this one, and this one is going to be 6 volts. That was my previous video on series in parallel. Okay, so that's the diagram I just showed you. Now I'm showing you it as a stair-step diagram, but batteries raise it by 6, and each resistor is going to drop it by 6. Okay, so like with this Ohm's law, if I know 2 of the variables, I can find the third. So we've got 6 volts, or this is going to get 6 volts and 6 ohms. This one's going to have 1 amp of current running through it. This one gets 6 volts, but it's on 3 ohms, so there's going to be 2 ohms, 2 amps running through that one. 6 volts and 2 ohms, there's going to be 3 amps running through that one. So if there's 3 amps through that one, 2 amps through that one, and 1 amp through this one, there's going to be 6 amps altogether. So anytime before it branches, before there's a junction, there'll be 6 amps. So we've got 6 amps running through the battery. 1 amp is going to go through here, 2 amps are going to go through there, 3 amps are going to go through there, but we've got all 6 amps running through right there. Another way we could have done that to find the 6 amps is by finding the total resistance. Now the total resistance in parallel is 1 over 6 plus 1 over 3 plus 1 over 2. You get an answer. That answer is equal to 1 over the resistance in parallel. And then you take 1 over that answer, and you find that it would just be 1 ohm of resistance altogether. Those 3 resistors in parallel have an equivalent resistance of just 1 ohm. So 6 volts with just 1 ohm of resistance is going to be 6 amps altogether. Okay, we found it 2 different ways. Finding the total resistance or adding up the individual currents. This one is a little more complicated. This one's going to require that we really think about it carefully. And if you were to just jump in here and try to do this without visualizing these stair steps, it could be quite confusing. So I'm going to redraw this schematic diagram as stair steps. But when we're done with it, we want to measure how much current is running through there, here, there, and there. We use A because we're going to place an amp meter there to measure the current. And we'd like to measure the voltage drop across each resistor. Looks complicated. So here we go. That's what I just showed you. And we see that we have the blue one and the green one in series with each other. That's these 2 right here. Those 2 were in parallel with this one. That was right here. And then those 3 are in series with this one. So those 3 are in series with this one. And we would like to figure out how much voltage this one gets, each of these, and how much current is running through each one. Just like we did before, we found the total resistance first. That really is going to help us to solve this problem. Well, I'm going to chunk it down to say this is 3 ohms and 2 ohms in series with each other, so that has an equivalent of 5 ohms. So the parallel part, you take 1 over 8 plus 1 over 5, you get a decimal value. That decimal value is equal to 1 over the total resistance in parallel. So then you have to take 1 over that decimal to get the total resistance in parallel. So that's just this part right here. That's the total resistance of that. But that is in series with this one. So you just take the equivalent that we found from here, add it to the 6 ohms here, and we get a total resistance for the whole circuit of 9.08 ohms. And I think it's fairly safe that if you find the total resistance of the circuit first, you're not going to go astray. It's probably the first thing you want to do on most problems. Because now that we know we have a total resistance of 9.08 ohms with a total voltage of 12 volts, we can find out how much current there's going to be in total. So all along here and all the way up to right here, we'd have 1.32 amps. From here all the way to over here, we would also have 1.32 amps. The current only changes when it branches and splits. So I'm going to have 1.32 amps running through that single resistor. Well, just like with Ohm's law, if you know two of the variables, you can find the third. I know the current, I know the resistance, so I can figure out how much voltage drop that gets. It had this much current, it had that much resistance, so that resistor is going to drop the voltage by almost 8 volts. All right, so now we've found current and resistance through this one. We still need to find current and resistance through those three. This is where the stair steps really help us out, because this raised it by 12. We just found that this dropped it by 7.93. So this should drop it by the difference of 12 and 7.93. And we find that it was 4.07. This is going to drop it by 4.07. This, we found, dropped it by 7.93, a total drop of 12, because there was a total raise of 12. But now that I know the voltage on this resistor and the resistance, I can find the current. It had this much voltage, it had that much resistance, it's going to get this much current. All right, now I'd like to find how much current is running through here so that I can find how much voltage this one gets and how much voltage that one gets. This is where Kirchhoff's Junction Rule is going to come into play. This 1.32 amps was all running along here. Some of it went this way, some of it went that way. We know that we have 1.32 amps total, and we just found that 0.508 amps come this way. So I should be able to figure out how much came that way by subtracting those two. What's left over has to come through this way. So I've got 0.814 amps running through this resistor right here. Well, these are in series, so I have to have 0.814 amps running through that one as well. The current only changes when it splits. Now that I know how much current is running through that resistor, current and resistance, I can solve for voltage. That was using Ohm's law. This is how much voltage that resistor gets. And then I'm just going to do the same thing for this one. I know how much current was running through that resistor, and I know its resistance, so current equals voltage divided by resistance. I solve for the voltage, and that's how much voltage this one gets. If I took 1.63 and I added to it 2.44, this drop plus this drop, you're correct, it should equal this drop, because it started at this level, ended up at this level, each must have dropped it by the total amount. That might need a brain break, but we're going to go on, or you hit pause if you need, but I'm going to go on with my video. When we're dealing with batteries, there's one small complication with batteries, is that they don't provide a constant amount of voltage. If I were to just take a battery and measure the voltage from either side of the battery, that would be the EMF of the battery, the electromotive force that provides voltage. A D-cell battery should provide 1.5 volts of potential. Those little square batteries are 9-volt batteries, provide 9 volts. Okay, so that's the EMF of the battery, the electromotive force that provides voltage. And I should measure that when there's no current running through that resistor, or running through the battery. But batteries have internal resistance. It's unavoidable. Just the electrons can't perfectly freely flow through a battery. So not only does a battery provide EMF, it also has some resistance. And when you send current through a resistor, it drops the voltage. So as soon as I hook that battery up to a circuit and let things flow through here like this, I'm actually hooking it up just to 2 resistors in my diagram. This resistor, I'm saying, is internal resistance, is that little resistor that's inside the battery. So when you send current through a resistor, it drops the potential. This battery now kind of comes to this level because this much energy was used due to sending current through that resistor. And that's why batteries get warm when they're used. All right, let's look at it this way. And I'm going to teach you in just a moment how to use multimeters to measure this. But here is a 9-volt battery. Actually, it's an 8.7 volt battery. And this battery is not connected to those light bulbs. There's no current running through that battery. So this 8.70 volts is the EMF of the battery, the full potential of the battery. There was no current to drop that resistance. So the EMF of the battery and the voltage of the terminals would be the same. Now we're going to connect those alligator clips to just one of these light bulbs, and everything else was measured the same, but this time I'm measuring 4.65 volts with that battery, and it had 0.407 amps. The inside voltage of the battery didn't change. It was still 8.7, but because I had current running through a resistor, it dropped the voltage. And if I solve for that, I find that it was about 10 ohms of resistance for that battery. Here, now I have both of those light bulbs lit up, and they're not quite as bright because current could come this way, current could come that way, and I had more current than what I did here. The same EMF of the battery, but this time, because so much current was running through that battery, the internal resistance dropped a lot here, and I'm only getting 2.75 volts of terminal voltage. And that would say that the battery had, when I solve for this variable here, had 10.1 ohms of resistance. Let me just apply quickly Kirchhoff's loop rule to a problem you might see here. This is the symbol for a battery. Long is positive, short is negative. When current goes through the battery in the normal direction, it will raise it. When current goes through in the opposite direction, it will drop the potential. So I'm saying there's an open circuit here. If I were to measure across C and D here, what would I measure? Well, Kirchhoff's loop rule says around any loop, the total raise should equal the total drop. So I'm going to be measuring the voltage across C and D. I'm going around this direction because I'm going from C to D. So if I go around the loop like this, this would be dropping by 7. I'm going against its normal output. So a drop of 7 and a raise of 2, a drop of 7 and a raise of 2, plus whatever this is, should equal 0. There should be no net difference. When you solve for that, you find that this voltage here, across here and here, should be 5 volts. So it's just like there's a battery there that's 5 volts in the normal direction of output. Now that we found that one, let's go ahead and find out what we would measure if we measured from this time B to A. So I'm going to go around my loop like this, from B to A. So that is going to be a positive 8, a positive 5, and a minus 4, because we're going the opposite direction of that. Positive 8, positive 5, and minus 4. We solve for BA, and we get minus 9 volts. That would be just like if we put a 9-volt battery in there, but in the opposite direction that it normally goes. Now I want to quickly teach you how to measure voltage and current with an amp meter. So let's do, excuse me, let's do voltage first. We have 4 holes to plug this into. We always plug one into the common, and then we have a decision which hole to plug the other one into. This hole is labeled, you see the omega symbol and the voltage symbol. So we would measure this, we'd plug it into this hole if we're measuring resistance or we're measuring voltage. These charges have energy. So before they go in, they have some energy. After they go through the resistor, they have less energy. It's dropped the potential. So when we're measuring a multimeter here, we really can just touch on either side of the light bulb and measure how much the voltage has changed. So a voltmeter is measuring the change from here to there, or how much it dropped the potential. It's pretty easy to use a voltmeter. You just touch on either side. And one thing we have to understand about these two holes here is that between these two holes there has to have a lot of resistance. It must have a lot of resistance, otherwise if we touched through here to here, the current would a lot more current would go through the resistor here, the multimeter. So this has to have a lot of resistance so you don't get current running through that way. I'd like to measure the current through right here. So this one's a little more challenging. We're still going to plug a alligator clip or a banana plug wire into the common, but we still have our four choices here. We're going to be measuring current with an ammeter, so we're going to plug it into this one. If we were measuring really small amounts of current, like milliamps or microamps, we would plug into this one. So the current is running through here, and we have two wires. How do we connect our two wires so that we can measure how much current is going through right there? If we plug both our wires in right there, not much is going to happen. What we got to do is we have to open up the circuit, divert all that current, make a detour here, so that whatever current is running through that light bulb, it is also running through the ammeter so that the ammeter can count the charges. When you measure amperage with an ammeter, you have to open up the circuit and get all those charges through there. You have to make a detour. Now here's the thing that's important here. Between these two holes there has to be extremely little resistance, because if you put this resistor in series with this, you would increase the total resistance if that had any appreciable amount of resistance. So if this had resistance, you're going to increase the total resistance, and increasing the total resistance would lower the amount of current. So the mere act of trying to figure out what the current was would change what it was. So we really have to have negligible amount of resistance right there. This is a mistake students often make, is that they plug it into here and here, they touch on either side there, and because this has such little current running through there, you're going to get a massive amount of current. Because we had such little resistance here, we're going to get a massive amount of current running through there, and it will actually blow up the multimeter. Well, it doesn't actually blow up the multimeter. Fortunately, there's a little fuse in there, and when too much current runs through that fuse, it blows up the fuse like this. That fuse melts and it breaks the current here. But if you got something plugged into that hole, don't touch on either side of this. You have to open up the circuit and make a detour. So if you had a circuit like this and you want to measure the current right there, figure out how many charges go by there every second, you've got to open up the circuit, detour all those charges through the ammeter so that it can count it, and then deposit it back onto the circuit so they can go on their merry way. And that is all I have for measuring current and voltage in direct current circuits.